Hello, friends. Thanks again for joining us in this series. So previously, in the first series, in the optics, the Converging Lens series, we talked about terminology and sign convention. Please check it out if you haven't. And in this series, we went over 2 videos describing the image and the techniques for ray tracing for objects outside and inside the focal point. All right. And now in this one, we're going to do a couple exercises, work through the thin lens equation, and then do the the ray tracing, just to see if we can verify the results. So again, thank you for joining us. Please like, subscribe, share if you find this information really helpful, comment on our work, and let's begin. All right, so we have a 2-centimeter tall object placed 45 centimeters to the left of a diverging lens with a focal length of 15 centimeters. Let's describe the image. All right, so this object is going to produce a virtual image, and it should be inside the focal point. So let's go ahead and let's see first, write down what we're given. Okay, that's always a good starting point. So we are given object DO is 45 centimeters. The focal length, it's negative 15 centimeters. Yes, they said it's a focal length of 15 centimeters, but the fact that it's diverging right here, we have to put it ourselves negative 15 centimeters. And that's all we know. Okay. Now from these two, we can get the distance to the image, which now we can get the magnification. We know the focal length, we can easily get the power, already. So let's go ahead and work this one out. So first, let's get DI. So we need DI, we need M, and we need power. Those are all unknowns. Okay? So start with the lens equation. Let's put DI on this side. Equals 1 over F. Bring DO over. So 1 over DI is 1 over F minus 1 over DO. Get a common denominator. F times DO, and here we have DO minus F. Okay? Again, if you're not sure about this math, A over B minus C over D. You multiply these two. Then D times A. This is what you start with, okay? Don't start with B times C. It's D times A, or A, if you want to go this way, maybe. Start on the top left and go down. So A times D minus C times B. Same thing here. So DO times 1 is DO minus F times 1 is F. Okay? It's a good thing to remember. All right. And now we flip. So DI is F times DO over DO minus F. Let's plug numbers. F is negative 15 times DO, which is 45, over DO, again, is 45 minus negative 15. So negative 15 times 45 over, these negatives give me a plus, so it's like 45 plus 15 or 60. So what do we have here? The 15 and the 60 give me a 4 in the denominator. So I have a negative 45 over 4 centimeters. Okay? And that is the distance to the image, 4 right here, and it's negative, which is good. We want it to be negative. And this is actually negative 11.25 centimeters. Okay. So let's look at the power now. Oops. Don't allow for room. Let's do power here real quick. So power. Power is 1 over F. Okay. Well, that doesn't describe the image, but we can talk about it here. And F is in centimeters. So again, let's put F in meters first. So F is negative 15 centimeters, which is negative 15 over 100 meters. Okay? So easily divide by 5. So negative 3 over 20 meters. So now P is 1 over F, 1 over negative 3 over 20, which is going to be negative 20, close to the edge there, negative 20 over 3 diopters. All right? And real quick, let's look at magnification. So M equals negative DI over DO. So DI is negative 45 over 4. So it's negative 45. Let me write it better. Divide by DO, which is 45. So the 45s cancel out, and I get a quarter, or 25%. So if my image is 2 centimeters, a quarter of that is half a centimeter. So basically, right here, we could say HI is basically half a centimeter. Which is a quarter of 2 centimeters. So let's see if this and this match our, using ray tracing. Let's see if these are matched in the ray tracing solution. So here we go. So I should have taken it a little bigger, but this is good. So here's my object. Okay. And again, a ray that is parallel hits the lens, diverges as if it's coming from the near focal point. So each of these is 5 units. 5, 10, 15, and here's the 45. A ray going through the center continues unimpeded. A ray directed at the far focal point right here. The lens interrupts that ray, and the ray exits parallel. Okay? And now they all meet over here. Okay? So basically, if this is 2 units, this is a little bit less than a third of that. Okay? So we're almost there. Okay? Because it's a quarter, right? So if this is 2 centimeters, right? So this is a little bit less than a third. So roughly a third of 2 centimeters. It's almost a quarter. So we're almost there. Okay, this will be a third. This line is the third line. So we're doing good. Okay, and how about the distance? Here's 1, a little bit. This is 10. So it's closer to 10 than 15. So maybe 11. And this one is looking like it's 11. And what did we get here? We got 11 and a quarter. Okay. So we're okay. Again, these are all estimates with the ray tracing. Unless you really have, you're doing, exact distances, ruler and everything. This is awesome. This is a good result. All right. So that's how we do it for this problem. Let's build this and move on to the next problem. So now we are given a lens with a power of -5 diopters. So again, the diopters, P, is -5, which is 1 over F. So F is -1 over 5. We're solving for F from there, or -0.2. That's in meters, which is -20 centimeters. So we know the focal length. That was given in the first few words. We have a virtual image 10 centimeters away from a diverging lens. And the fact that it's diverging, they didn't have to say diverging lens, right? And they didn't even have to say a virtual image. The fact that the power is negative, automatically it tells you it's a diverging lens because the focal length is negative. Okay. And a diverging lens always gives you a virtual image. Okay. So virtual image 10 centimeters away from the lens. So now DI is -10 centimeters because again, it's virtual. So we need to find DO and M. What are these equal to? Okay. So as usual, we start with the thin lens equation. So 1 over DO plus 1 over DI is 1 over F. Bring the DI over to the right. 1 over DO is 1 over F minus 1 over DI. Let's take it up here. So get a common denominator. That will be F. And then here DI minus F. Okay. Flip them. Let's plug it in. Now DO needs to come out positive. Okay? Because again, that's the image. So whatever math we do here, we're expecting DO to be positive and farther to the left than the image. So the image is 10, DO has to be at least 10 to the left. So let's plug numbers in. So here's -20 for the focal length. For the distance to the image is -10. Here I have DI is -10 minus DO. I mean F. F is -20. On top, I get 20 times 10. The minuses cancel out. At the bottom, I get -10 plus 20. So I get 10. 10s cancel. I get 20 centimeter. All right? Which is good. It is positive, and it's to the left of my image. All right? So now let's look at, so we got the object's location. Let's look at the magnification. M is -DI over DO. Negative. DI is -10. DO is 20, which is a half. First of all, it's good because it's positive, and then also it's less than 1. Because as we saw in the first video in this series, when we did the lab and we swept the the object all the way from the left side and we went closer to the lens, the image was always smaller than the object. And if the image is always smaller than the object, as a matter of fact, I think I have that pulled up over here. Let's see. There it is. Here's a lens. Let's go to a diverging lens. And arrow. And let's see. If we sweep it again, from all the way here, inwards, look at the image. The image is always smaller and to the right of the object, even as I come closer. Okay? So the fact that the magnification is less than 1, that means the image is smaller than the object. Positive, that the image is pointing up. Okay? Now let's verify this with our ray tracing. Okay? So let's see. Here's the image. And then here's the object. So first of all, this is 3 units. This is the object, I'm sorry, and here's the image. The object is 3 units. The image is roughly at 1.5, half of that, which verifies this. It is pointing up, so the magnification is positive. Now let's go through those rays again. The first ray coming in parallel, right here, leaves the lens as if it's coming from the focal point. Okay? And if we go back, the focal point was at negative 20 centimeters, and the distance to the object was at 20. So they're on top of each other. That's why we see them here on top of each other. Okay? The second one is the green one. It goes through the center and then exits undeflected. And the third one, it appears as if it's going to go through the far focal point, but it comes out parallel. And they all meet back here. And this is my image right here. So this is the ray tracing. And now the image is at 10. So, and the focal length is at 20, and the object is at 20. So again, parallel ray leaves the lens as if it's coming from the near focal point. Ray, as if it's going to go through the focal point on the other side, leaves the lens parallel to the axis. A ray through the center or the vertex just keeps going. And they all meet on this side, and this is half this. The image is half the height of the object, and it's, again, at the 10 centimeter mark. That's at the 20 centimeter mark. All right? So this is good confirmation. And this is all for this video. In the next one, we'll do more exercises relating to diverging lenses. Hope to see you there. Thanks. Bye-bye.